The Shadow Biosphere Hypothesis. At the heart of our understanding of life on Earth lies an assumption we rarely challenge. Humans are the pinnacle of intelligent evolution, the first species to possess advanced tools, language, and culture. But what if this belief, so deeply rooted in our understanding of history and science, is wrong? What if humans were not the first intelligent species on Earth, but simply the most recent in a long line of civilizations that have come and gone, their traces buried beneath layers of geological time? This question, though deeply unsettling to our human-centric worldview, is at the core of the Shadow Biosphere Hypothesis. The hypothesis suggests that Earth may have hosted other intelligent species before humanity's species that were technologically advanced, biologically different, and perhaps even capable of altering the planet's ecosystem on a global scale. These ancient civilizations, however, could have left no obvious signs of their existence, their impact erased or disguised by the vast forces of geological time. The idea proposes the shocking possibility that other, more elusive lifeforms might have coexisted with or even predated the emergence of Homo sapiens, hidden in plain sight under the guise of natural phenomena we have yet to fully comprehend. The Shadow Biosphere suggests that Earth's biodiversity includes not only the life forms we can observe, but also others that may be fundamentally different from everything we currently understand about biology. It challenges the conventional model of evolution, where life forms evolve through a clear path of complexity from simple organisms to the diverse array of species we observe today. What if Earth's history includes entire ecosystems or even intelligent species that have left behind no fossil record because they were based on biochemistry unlike our own? Could there be life forms that evolved using alternate building blocks, invisible to us in our traditional search for carbon-based life? The quest for extraterrestrial life, most famously exemplified by projects like SETI, Search for Extraterrestrial Intelligence, has expanded our understanding of what life can look like in the universe. But the search has always been predicated on the assumption that alien life must fit our known criteria: organic, carbon-based, and recognizable through our existing scientific frameworks. What if, in the process of searching for life beyond Earth, we have missed the existence of another form of life right under our noses? A life form that evolved along a different biological path, and whose signs we simply do not know how to detect. This is where the Shadow Biosphere Hypothesis becomes both provocative and unsettling. It suggests that remnants of intelligent life, perhaps millions of years older than humanity, could have coexisted with us on this planet, possibly even thriving in parallel with our ancestors, before being driven into extinction or fading into the background of Earth's natural systems. These life forms might not have been made of the same substances we are familiar with. They might not have left behind the telltale fossils or DNA that we associate with ancient life. Instead, they could have left behind subtle, almost imperceptible traces, signatures so faint, so alien to our understanding of biology, that we overlook them, dismissing them as nothing more than natural geological or chemical processes. The idea of a shadow biosphere challenges one of the most fundamental assumptions in the study of life on Earth: that life as we know it is the only kind of life that has ever existed, and it forces us to reconsider the boundaries of what constitutes life and intelligence in the first place. Imagine for a moment that Earth has hosted not just one, but several intelligent species, each one leaving behind its legacy in ways so subtle that we can't yet recognize them. If we look closely at the physical and chemical records embedded in the Earth's rocks, oceans, and atmosphere, could there be clues hidden beneath the layers of time that point to long-lost civilizations? Fossil records, typically used to reconstruct the evolutionary story of life on Earth, might not be telling the full story. Could the absence of fossil evidence in certain periods indicate something other than a gap in our understanding of evolution? Could it be that entire branches of intelligent life existed and vanished without leaving any trace that our current scientific methods can detect? What makes this hypothesis so compelling is the staggering scale of geological time. Earth's history spans over 4.5 billion years, and modern humans have only existed for a tiny fraction of that time, around 200,000 years. But in that brief span, we've managed to alter the entire planet, from the atmosphere to the landscape. Our tools, cities, and even our plastics will leave an imprint on Earth for millions of years to come. Now imagine if there were civilizations that existed long before us, with technology far surpassing our own, but whose traces have been erased by the very forces of nature that shape our world. If we are the first intelligent species, then why do we find so many mysterious gaps in the fossil record? Why do we find evidence of extinction events that seem too sudden or too precise to be explained solely by natural processes? To understand why the Shadow Biosphere Hypothesis is so radical, we must first look at the scale of deep time. If humanity's technological civilization were to vanish tomorrow, what would remain of our presence on Earth in 1,000,000 years? Our buildings would crumble, our plastics would degrade, and our bones would disintegrate. Yet the isotopic traces of our industrial activities, the burning of fossil fuels, the scattering of plastics, the nuclear tests would remain. These chemical signatures would persist in the atmosphere, in ice cores, and in the soil. But what if previous civilizations, much older than ours, used technologies that we don't yet understand or that we have failed to recognize? To further understand the concept, consider the Cambrian explosion, an event roughly 540 million years ago, when life on Earth suddenly diversified in a way that the fossil record cannot fully explain. Thousands of new species appeared seemingly overnight, without clear evolutionary precursors. If we accept the idea that life as we know it could evolve from simpler organisms into complex multicellular creatures, could the Cambrian explosion be a clue to a lost history? Could the sudden burst of diversity in the fossil record be evidence not of natural evolution, but of intelligent intervention or influence by a now vanished species? What if the fossil record, with its gaps and missing links, does not just reflect an incomplete story of evolution, but rather a story of civilizations lost to time, each one contributing to the complexity of life on Earth in ways that we do not yet recognize? These questions force us to think beyond the traditional boundaries of biology and archaeology, and to reconsider the possibility that human beings might not be the first intelligent species to walk the Earth. A world already shaped by unseen forces. As we delve deeper into the Shadow Biosphere Hypothesis, we begin to confront a stark possibility. Earth may not be the pristine cradle of life that we have always believed it to be. For centuries, we've assumed that the planet's ecosystems, geochemistry, and fossil records represent a natural, straightforward progression of life, from simple organisms to the advanced beings we see today. But what if this natural narrative is incomplete? What if the evidence of intelligence and civilization is already embedded in the very fabric of the Earth, but we fail to recognize it because we are looking for the wrong signs? The Earth beneath our feet is alive with clues, many of which remain elusive. While we tend to think of life in terms of carbon-based organisms, those that rely on DNA, cells, and oxygen, what if the true legacy of past intelligent species is hidden in plain sight, camouflaged by our limited understanding of what life could have been? What if Earth's surface is teeming with enigmatic, unseen forces that subtly influence the development of the planet's geology, atmosphere, and ecosystems, forces that trace back to intelligence we can't yet comprehend? One of the most perplexing aspects of the Shadow Biosphere Hypothesis is that it forces us to consider the idea that the natural processes we observe today, the geological formations, the chemical processes, the fossil records, might not solely be the result of natural evolution and geological forces. Instead, these processes may be shaped by intelligent actions, long forgotten, that once molded the planet itself. If intelligent life existed here millions of years ago, what traces might they have left behind in the form of chemical anomalies, isotopic signatures, or unusual patterns in rock formations? In many ways, the anomalies that seem to challenge our current understanding of the Earth's history are the very clues that support the idea of past intelligent species. One of the most fascinating examples of this is found in the study of unusual chemical signatures. Geologists have long understood that certain elements such as carbon, oxygen, and nitrogen play fundamental roles in Earth's ecosystems. However, when scientists look at the isotopic compositions of certain geological formations, they have encountered strange patterns that seem to indicate that some past event caused a massive systematic shift in the Earth's atmosphere or surface conditions. For instance, scientists have discovered unusual isotopic ratios in ancient rock layers that are strikingly similar to those produced by industrial activities, specifically the combustion of fossil fuels or nuclear explosions. These isotopic anomalies are found in rock formations that date back millions of years, far before humanity began using coal or uranium in significant quantities. One of the most perplexing examples of this is the presence of carbon isotope ratios in rocks from periods like the Permian-Triassic boundary to 152 million years ago. a time when life on Earth was decimated by a series of catastrophic events. These ratios suggest the combustion of massive amounts of carbon, perhaps from large-scale industrial activity, long before humans appeared on the scene. What makes these discoveries so intriguing is the precision with which these chemical signatures occur. When humanity began industrializing, we left behind our own distinct isotopic footprints in the Earth's atmosphere, primarily in the form of increased carbon dioxide and methane levels, as well as radioactive elements from nuclear tests. But to find similar anomalies buried in rock layers from hundreds of millions of years ago challenges the conventional wisdom that such events are only a modern phenomenon. Could these anomalies point to past civilizations that engaged in large-scale industrial activities, altering our planet in ways we have yet to fully understand? Another compelling clue lies in the mystery of mass extinction events, which have periodically wiped out vast swaths of life on Earth. Traditionally, scientists have attributed these events to natural phenomena, such as asteroid impacts, volcanic activity, or dramatic climate changes. However, the timing and precision of certain extinctions suggest something more deliberate, more calculated. Could intelligent beings have played a role in orchestrating these catastrophes, either intentionally or accidentally? The Permian-Triassic extinction event is a prime example of this. While the commonly accepted explanation attributes the event to massive volcanic activity, the fossil record shows signs that suggest a highly targeted, selective form of extinction. Certain species disappeared with remarkable precision, while others that would logically be more vulnerable survived. This selective nature of the event raises the possibility that it was not simply a random natural disaster, but rather the result of advanced technological interference, whether through biological warfare, atmospheric manipulation, or other methods we cannot yet conceive of. If an ancient civilization existed with the capability to manipulate the planet's ecosystems at a planetary scale, it's possible that their actions could have triggered this event. Similarly, the Cretaceous-Paleogene extinction event, which wiped out the dinosaurs, has long been associated with an asteroid impact. But recent studies suggest that the asteroid may have been deflected or altered in its path, perhaps unintentionally, by some form of technological intervention. The idea that past civilizations could have possessed technology capable of altering the trajectories of celestial bodies is an unsettling thought, but one that gains traction in light of certain unusual features in the geological record. Could this be evidence of a time when Earth's destiny was shaped by forces beyond our comprehension? Even more perplexing are the gaps in the fossil record itself. Earth's fossil record is a patchwork of evidence, some of it rich and detailed, other parts disturbingly absent. There are periods in Earth's history where life appears to advance in a sudden burst, the emergence of complex life forms happening too quickly to align with the slow, gradual process we normally associate with evolution. This phenomenon, most famously known as the Cambrian explosion, saw an explosion of complex life forms, organisms with hard shells, eyes, and intricate body plans emerging in a relatively short time frame. According to traditional evolutionary models, such a sudden burst of complexity should have taken millions of years. Instead, it happened in a geological blink of an eye. This rapid diversification of life forms could be a natural evolutionary leap, but it could also be a product of external forces. If an intelligent species had previously existed on Earth, could their influence have triggered or accelerated the Cambrian explosion? Could genetic manipulation, either intentional or accidental, have pushed the evolutionary clock forward, fostering new forms of life that would go on to dominate the Earth? Moreover, the absence of certain fossilized species, combined with the sudden appearance of new forms, raises a crucial question. What happened to the life forms that existed before this explosion? Could there have been species so different from today's animals, species we might consider highly intelligent, that vanished without leaving a trace? Could these species, despite their intelligence, have been biologically incompatible with the forms of life that emerged afterward, and were thus erased from the record entirely? If intelligent species once existed on Earth, their existence may not be obvious to us in the ways we expect. The key to uncovering their legacy lies in looking beyond the obvious signs, the fossilized bones, the traditional chemical markers, and instead focusing on the subtle hidden traces that remain. These could include isotopic anomalies, strange fossils, altered patterns in the atmosphere and oceans, and perhaps most intriguingly, the unrecognized signs of technological activity embedded within Earth's geological strata. The possibility of a shadow biosphere, a world where the traces of past intelligent species remain locked away, hidden from view by the veil of time, forces us to reconsider everything we know about the evolution of life on Earth. It suggests that the planet's history is far richer, far more complex, and far more mysterious than we have ever imagined. The truth may not lie in what we have discovered, but in what we have overlooked, silent witnesses to the rise and fall of civilizations we have yet to acknowledge. The search for life beyond Earth, a precedent for detection. As humanity embarks on the grand quest for extraterrestrial life, we often look outward toward the stars. Telescopes peer into the distant cosmos, scanning for radio signals, chemical markers, and patterns that might suggest the presence of intelligent life on faraway planets. Yet, in the shadow of these grand ambitions, a quieter and perhaps more perplexing question arises. Could life intelligent and complex have already existed right here on Earth, long before we ever looked to the heavens for answers? In our search for alien civilizations, we've adopted a well-established methodology, the tools we use to hunt for extraterrestrial life, primarily those developed through the Search for Extraterrestrial Intelligence, SETI, are built on the assumption that alien life will fit into our traditional understanding of biology. SETI uses radio telescopes to search for electromagnetic signals that may be transmitted by distant intelligent beings, hoping to catch a glimpse of advanced civilizations communicating across the vast distances of space. We also study exoplanets, analyzing their atmospheres for chemical signatures of life, such as oxygen, methane, and other gases that could point to biological activity. What if we have been looking at life the wrong way? What if the signs of life, especially intelligent life, are not so easily detectable, and in fact they might have been right under our noses all along? This is where the Shadow Biosphere Hypothesis challenges our conventional approach to the search for life. If an advanced species or ecosystem once existed on Earth, but used a completely different biochemical foundation, its signs may be beyond our ability to detect. Just as we search for signs of alien life in distant galaxies using methods suited to our understanding of biology, perhaps we need to apply similar techniques to search for signs of alien life on Earth, life that may have evolved in parallel with us, but left no obvious traditional trace. The tools and methods we currently use to search for life on other planets are based on assumptions rooted in Earth's biology. We search for biosignatures, the chemical markers of life, like oxygen and methane, which are abundant in the atmospheres of our own planet. However, these markers are based on a single form of life that is carbon-based, oxygen-breathing, and metabolizes energy in ways we understand. But what if alien life forms don't follow these rules? What if, instead of searching for familiar biosignatures, we need to expand the scope of our search to include entirely unknown forms of biological and chemical activity? If previous civilizations existed on Earth, they may have left behind chemical signatures that do not fit into the molds we use to detect life today. The search for extraterrestrial life is already expanding beyond the traditional biosignatures we've been searching for in other worlds. Scientists are starting to consider biosignatures that could include non-carbon-based life forms or even life that doesn't rely on water as a solvent. Could these same techniques be applied to Earth to uncover the remnants of life forms that evolved with entirely different biochemical processes, ones that we have failed to recognize? Astrobiologists are already considering the possibility that alien life forms could be based on alternative chemistries, like silicon-based life, which could thrive under conditions vastly different from those found on Earth. On planets with extreme heat or cold, for example, life could exist in ways that challenge our understanding of what constitutes life. The same possibilities could apply to our own planet. Could there have been life forms on Earth that, instead of following the carbon-based chemistry that dominates modern biology, used other elements, silicon for instance, or even entirely unknown compounds as their biological backbone? This shift in thinking forces us to consider the implications for the shadow biosphere. If intelligent species have existed on Earth, they could have used chemical processes or biological markers so foreign to our current understanding that their traces remain undetected. Our current scientific framework simply isn't designed to recognize the possibility of life forms that do not adhere to the rules we've come to accept. But if we broaden our search, taking inspiration from the exploration of distant planets, could we begin to uncover the hidden signatures of life that once walked Earth? The history of science is full of examples where the unexplained has led to breakthrough discoveries. Microbial extremophiles, organisms that thrive in the most hostile environments on Earth, are one such example. These tiny life forms live in extreme heat, cold, acidity, and pressure. areas previously thought uninhabitable. The discovery of extremophiles forced scientists to reconsider the limits of life and fundamentally shifted our understanding of biology. Life, it turns out, is far more adaptable and versatile than we once thought. If life forms can survive in such extreme conditions, could the same principle apply to intelligent species that evolved in ways that do not fit within the narrow parameters of Earth's dominant ecosystems? The Shadow Biosphere Hypothesis suggests the possibility of hidden biomes, ecosystems that may have once existed on Earth, but were wiped out or concealed by geological processes over the course of millions of years. These biomes might have existed in environments that are difficult to study, like deep underground, in extreme cold, or in isolated, inaccessible regions of the planet's crust. These environments could have fostered life forms that, although intelligent and technologically advanced, left behind no obvious trace. What might these biomes look like? Imagine a world within our world, an ecosystem that flourished in the deep oceans, beneath layers of ice, or even within the Earth's crust. Could these biomes have housed civilizations with technologies that left behind no recognizable fossils or signs of activity? What if these civilizations used forms of energy or materials that have since degraded beyond recognition, or developed tools that leave no discernible impact on the geological record? One of the challenges in detecting the traces of past civilizations is that Earth's geological layers are constantly shifting and changing. Over millions of years, tectonic plate movements, erosion, and volcanic activity erase much of the evidence that could reveal an earlier history of intelligent life. However, the Earth's deep geological record contains many secrets still locked within its layers. Recent technological advancements, such as deep-sea drilling, ice core sampling, and geophysical imaging, are beginning to uncover the mysteries of Earth's past. What if buried deep within these layers, we find remnants of a long-lost civilization, whose influence on the planet was subtle but far-reaching? In many ways, the search for the shadow biosphere is a search for patterns rather than simple signs of life. The absence of fossil evidence is not necessarily proof that intelligent life never existed. It may simply reflect the difficulty of detecting traces left by species that were not biologically similar to modern humans. Just as modern researchers look for patterns in the electromagnetic signals from distant stars, we must look for new patterns in the geological record, in the chemical signatures of the Earth's past, and in the unexplained anomalies that persist in the environment. To find the shadow biosphere, we may need to expand our toolkit, embracing techniques designed to detect hidden, alternative forms of life that don't necessarily conform to our preconceptions. By doing so, we may just uncover the hidden history of Earth's intelligence and begin to piece together the remnants of civilizations that have come and gone long before humanity ever walked the planet. Unusual fossils and anomalies in the geological record. When we attempt to reconstruct Earth's deep past, the fossil record becomes our most direct line of evidence. Fossils provide snapshots of ancient organisms frozen in stone, allowing us to trace evolutionary lineages across hundreds of millions of years. Yet the fossil record is far from complete. It is patchy, selective, and full of mysteries that continue to baffle paleontologists. For those exploring the possibility of a shadow biosphere, or even the existence of intelligent species before humanity, these gaps and anomalies take on a new significance. Could they represent not just missing data but the remnants of life forms that fall outside of our standard biological expectations? Could some fossils, isotopic signatures, or strange mineral patterns point to entirely different ecosystems that thrived and disappeared long before our current biosphere came to dominate? The fossil record, while powerful, is an imperfect archive. Fossilization is an exceedingly rare process. For an organism to become fossilized, it must be buried quickly in sediment, shielded from scavengers, and preserved in conditions that allow minerals to gradually replace organic material. This means the vast majority of life that has ever existed left no trace at all. Soft-bodied organisms, microbial life, and species living in environments hostile to fossilization are almost entirely absent from the record. Even major lineages are often represented by only a few scattered remains. This incompleteness opens the door to possibilities. If most life is never recorded, how much of Earth's biological story remains invisible to us? Could there have been entire ecosystems, perhaps even advanced life forms that arose and disappeared without leaving behind recognizable fossils? For researchers interested in the shadow biosphere, this blind spot is not just an obstacle but a clue. The very fact that so much is missing suggests we may need new tools and frameworks to uncover what standard paleontology cannot. Even within the fossil record we do possess, anomalies abound. Paleontologists occasionally discover fossils that do not neatly fit into established evolutionary frameworks. Some specimens appear morphologically out of place, exhibiting traits that seem far more advanced or strangely divergent than their supposed contemporaries. Others show structural patterns that defy classification altogether. Consider the Ediacaran biota, a collection of soft-bodied organisms that flourished around 600 million years ago, just before the Cambrian explosion. These enigmatic creatures, ranging from frond-like impressions to quilted radial shapes, do not resemble any living organisms today. Some scientists interpret them as primitive ancestors of modern animals. Others suggest they represent a completely separate branch of life, possibly one that left no descendants. Could these be remnants of a shadow biosphere, a parallel experiment in biology that was later replaced by the familiar animal lineages we know? Similarly, anomalous microfossils have been found in ancient rocks that predate complex life. Certain filamentous or spherical structures, preserved in formations more than 3 billion years old, bear striking similarities to microbial cells, but lack definitive chemical signatures. Some argue these are the earliest evidence of life. Others contend they could be abiotic mineral formations. The ambiguity raises tantalizing questions. Could these represent alternative biochemistries that our current tools fail to recognize? Beyond physical fossils, geologists and paleobiologists study chemical and isotopic signatures preserved in rocks. These provide indirect evidence of biological processes. Carbon isotope ratios, for example, can indicate photosynthetic activity, while sulfur isotopes can reveal microbial metabolism. Yet here too, anomalies exist. For instance, certain carbon isotope excursions in the Precambrian record show fluctuations so extreme that natural explanations are still debated. Did they represent massive biological blooms, unusual geochemical cycles, or something else entirely? Similarly, banded iron formations, layers of iron-rich rock deposited billions of years ago, suggest vast shifts in atmospheric chemistry, possibly tied to microbial life, but the exact drivers remain uncertain. Some researchers speculate that these anomalies may represent biochemistries fundamentally different from modern life, potentially tied to forms of life that no longer exist. Mineral anomalies also raise questions. Unusual crystal structures, rare trace elements, or unexplained concentrations of certain metals can sometimes indicate biological mediation. For example, modern microbes are known to influence the deposition of minerals such as pyrite or magnetite. If extinct life forms used alternative metabolic pathways, they might have left behind mineral signatures that appear odd or inexplicable by today's standards. Perhaps the most striking anomalies are not the fossils we find, but the gaps that separate them. The Cambrian explosion, occurring about 54-51 million years ago, saw the rapid emergence of most major animal groups within a geologically short window. Fossils before this event are sparse, dominated by enigmatic Ediacaran forms. Afterward, a stunning diversity of complex animals suddenly appears. Evolutionary theory can explain much of this as an interplay of environmental triggers, genetic innovations, and ecological interactions. But the abruptness of the transition continues to puzzle scientists. If we entertain the Shadow Biosphere Hypothesis, one provocative idea emerges. Could the Cambrian explosion reflect not just a burst of evolutionary innovation, but also the collapse or replacement of a prior biosphere? If so, the strange gaps in the fossil record may be less about missing data and more about hidden histories, overwritten by the rise of our current biological paradigm. Skeptics rightly caution against leaping to conclusions. Many anomalies in the fossil record ultimately find conventional explanations as new discoveries and methods emerge. Apparent outliers often turn out to be transitional forms, preservation artifacts, or misunderstood variations. Yet the persistence of ambiguity, especially in the earliest chapters of life's story, remains a fertile ground for new hypotheses. Could life have evolved differently? When we talk about life on Earth, we are talking about one particular solution to the puzzle of existence: carbon-based organisms powered by water, fueled by the energy of the sun, and organized around the same basic building blocks: DNA, proteins, lipids, and sugars. For us, it feels almost inevitable, as if this were the only possible way that life could exist. But biology as we know it is shaped survivorship bias. We are studying the version of life that succeeded on Earth, not necessarily the only version that was possible. This is where the Shadow Biosphere Hypothesis takes on one of its boldest implications. What if life took parallel evolutionary routes, built on chemistries we don't fully recognize, and some of those paths survived long enough to shape Earth in ways we can still detect? To grasp this, we must return to the early Earth, a time when conditions were far from stable. Billions of years ago, the planet's oceans boiled with hydrothermal activity, its skies were choked with methane and carbon dioxide, and ultraviolet radiation bombarded the surface. Such a crucible, the chemistry of life was not preordained. Scientists now believe that multiple prebiotic chemistries may have competed before the dominance of modern DNA-RNA protein life. In fact, researchers studying pre-RNA worlds suggest that molecules like peptide nucleic acid, PNA, or throws nucleic acid, TNA, could have formed self-replicating systems, rivaling the earliest genetic material. These alternatives are not science fiction, they are molecules synthesized and tested in laboratories, showing they can indeed carry information and replicate under the right conditions. If they existed once, who is to say they could not have persisted in ecological niches that escaped our notice? Even within Earth's known biology, there are organisms that stretch the boundaries of what we thought life could be. Take extremophiles, organisms that thrive in conditions we would once have dismissed as incompatible with life. Some archaea live in boiling acidic springs at temperatures over 120°C, others metabolize sulfur instead of oxygen, or extract energy from iron, uranium, or even pure rock. Tardigrades, those tiny water bears, can survive in the vacuum of space, shrugging off radiation and extreme cold. If life is this versatile within one biochemistry, it raises the question: how versatile could life have been if different biochemical systems had taken root? Could an alternative biology, running parallel to ours, have evolved pathways invisible to traditional biology textbooks? One of the most intriguing avenues of speculation is silicon-based life. While carbon dominates our world, silicon has similar bonding properties and is abundant in Earth's crust. Silicon does not form the same diversity of stable molecules as carbon, but under high pressure, heat, or in non-water solvents, it might sustain complex chemistry. Imagine a form of life not powered by liquid water, but by ammonia or methane as a solvent, similar to the cryogenic seas of Saturn's moon Titan. While such ecosystems might struggle in today's Earth environment, could they have flourished in early epochs when the planet's chemistry was more alien than familiar? Parallel to this is the possibility of mirror life. All known life on Earth uses left-handed amino acids and right-handed sugars, a universal pattern called homochirality. But in principle, life could exist with the opposite orientation, right-handed amino acids and left-handed sugars. Such organisms would be invisible to our current detection methods, because our biochemical assays are designed to recognize our version of chirality. In fact, if mirror life once evolved, it might still persist in microhabitats, unrecognized because our tools are literally blind to it. The evolutionary implications are profound. Evolution is not a straight line, but a branching tree with countless dead ends. In the deep past, multiple proto-lives may have started, only for most to vanish. But what if some survived? Not in the limelight of ecosystems dominated by plants and animals, but in isolated environments, deep underground, or within mineral matrices where they remain shielded from our scrutiny. Could parallel evolution have led not just to microbial oddities, but to lineages we would struggle to classify as alive in familiar terms? Perhaps intelligence itself might not be unique to our biochemistry. Different forms of cognition could have emerged in parallel systems, only to be lost or hidden by the dominance of carbon-based life. This question grows sharper when we consider mass extinctions. 5 times in Earth's history, life as we know it nearly ended. Each event reset the evolutionary clock, wiping out dominant species and allowing survivors to diversify. Could one of these cataclysms have erased evidence of a non-human intelligent lineage, or provided an opportunity for shadow life to rise briefly into prominence before being pushed back underground, both literally and metaphorically? Just as mammals emerged from the shadow of dinosaurs, could shadow ecosystems have risen and fallen, hidden from the fossil record, because they were built on chemistries that fossilize poorly or leave unfamiliar traces? Modern science is only beginning to explore these possibilities. Astrobiology, originally designed to search for alien life elsewhere, is increasingly recognizing that Earth itself may host forms of biology. We have yet to categorize if even one alternative pathway survived into the present or left discernible traces in the past. It would force us to rewrite everything we think we know about evolution. The Shadow Biosphere Hypothesis challenges us to look harder, deeper, and with more flexible definitions of life. It suggests that Earth's evolutionary story may not be a single narrative, but a tapestry woven from multiple chemistries, some visible and others hidden. In this way, the question, could life have evolved differently, is not idle speculation. It is an invitation to recognize our blind spots, to accept that the tree of life we study may be just one grove in a vast, unseen forest. And perhaps, if we look closely enough, we may find that the shadows are not empty at all, but filled with echoes of lives that evolved on their own strange terms, in parallel with our own. Unseen histories, lost civilizations, or hidden ecosystems. The Shadow Biosphere Hypothesis challenges us to look at life not as a single linear story, but as a tapestry woven from many threads, some visible, others hidden. If microbial extremophiles hint at a living biosphere we can barely detect, then the next step is to consider whether such hidden life could have gone further, developing ecosystems, complexity, and perhaps even intelligence. Could there have been entire lineages of organisms that evolved in parallel with us, building structures, cultures, or technologies, only to vanish without leaving recognizable traces? The idea sounds fantastical at first, yet when we examine Earth's history, it becomes clear how much has been lost. More than 99% of all species that ever lived are extinct. Vast chapters of evolutionary history are preserved only in fragments, fossilized bones, chemical traces, or nothing at all. The survival of evidence depends heavily on preservation, and Earth is a restless planet. Tectonic activity recycles crust back into the mantle. Erosion, floods, and ice sheets strip the surface clean. Within just a few million years, even the grandest structures can vanish without a trace. Human civilization itself has existed for only a sliver of geological time. If humanity were to disappear today, most of our artifacts, buildings, cities, even satellites would erode, rust, or decay in less than 100,000 years. That is barely a blink in Earth's 4.5 billion year timeline. This perspective makes the question less absurd. If another intelligent species or complex biosphere once flourished, is it possible we have simply failed to notice their remains? Their records might not resemble our expectations. We imagine technology in the form of metals, plastics, or digital artifacts, but a parallel intelligent species may have used tools we cannot recognize. Perhaps they mastered biotechnologies, weaving organic materials into their world in ways that leave no fossil signature, or perhaps their intelligence was ecological rather than industrial, shaping entire ecosystems as their infrastructure, creating balanced biospheres rather than mechanical machines. To us, their legacy might look indistinguishable from a natural environment. The concept of a hidden ecosystem is even more plausible. Unlike intelligence, ecosystems do not require advanced tools or cities to demonstrate complexity. Whole nets of life could have thrived in parallel to our own, metabolizing with different chemistry, forming self-contained loops of energy and matter. If such ecosystems existed, they would not necessarily fossilize in recognizable forms. A silicon-based organism, for example, might leave behind mineral deposits that we mistake for ordinary geology. A nitrogen-based metabolism could dissolve into the atmosphere, leaving only subtle isotopic anomalies. When we dismiss these anomalies as noise or oddities, we may be ignoring the fingerprints of another biosphere. Consider the Silurian Hypothesis, proposed by NASA scientists Gavin Schmidt and Adam Frank in 2018. They asked a provocative question: if an industrial civilization had existed millions of years ago, would we even be able to detect it today? Their answer was sobering. After just a few 100,000 years, nearly all direct evidence would vanish. What might remain are subtle geochemical signals, spikes in atmospheric carbon, unusual isotope ratios, or unexplained layers of sediment markers that could just as easily be interpreted as natural fluctuations. This thought experiment aligns perfectly with the Shadow Biosphere Hypothesis. What if these markers are not merely environmental quirks, but relics of a vanished ecosystem or civilization that played by rules different from ours? Skeptics argue that without clear fossils or artifacts, such speculation risks drifting into pseudoscience. But science often begins with anomalies, phenomena that don't fit our current models. The sudden appearance of complex organisms during the Cambrian explosion, unexplained extinction patterns, or odd isotopic signatures in ancient rocks may be more than random puzzles. They could represent shadows of histories we haven't yet learned how to read. Just as archaeologists once mistook ancient structures for natural formations, we may be misclassifying evidence of parallel biospheres as ordinary geology. The broader challenge is one of perspective. We assume intelligence looks like us, builds like us, and leaves behind legacies we would recognize. But what if intelligence itself can take radically different forms? A species that communicates chemically through ecosystems, or organizes socially through microbial colonies, may never leave behind stone tools or metal artifacts. To detect such civilizations, we must broaden our definition of evidence. Instead of looking for pyramids or pottery, we may need to look for unusual biochemical cycles, patterned ecological changes, or anomalous mineral deposits. There is also the possibility that shadow life persists today, not as a lost history but as a hidden present. Entire ecosystems of alternative life forms could still thrive in remote niches, undetected because we do not know how to see them. They may not compete directly with known life, but coexist in parallel, influencing our world in ways we interpret as natural phenomena. If this is true, then the lost civilization is not truly lost. It is merely unseen, woven into the background fabric of Earth's biosphere. The mystery of the Cambrian explosion. Among the greatest enigmas in Earth's biological history, the Cambrian explosion stands as a defining yet perplexing event. Roughly 51 million years ago, in the span of what is geologically considered a short period of about 20 to 25 million years, life underwent a staggering transformation. Nearly all the major animal phyla body plans that persist to this day appear suddenly in the fossil record. Organisms with eyes, skeletons, segmented bodies, and appendages arose seemingly out of nowhere, leaving paleontologists both awed and puzzled. From the perspective of the Shadow Biosphere Hypothesis, the Cambrian explosion may be more than a sudden surge in evolutionary innovation. It may represent the interplay between visible life and the hidden or parallel biospheres that preceded it. The classic interpretation suggests that environmental, genetic, and ecological factors combined to ignite this diversification. Rising oxygen levels, genetic innovations such as the evolution of Hox genes, and predator-prey dynamics are commonly cited as drivers. Oxygen allowed larger bodies and more complex metabolisms. Hox genes provided the developmental flexibility to experiment with new forms, and predation created a selective pressure that rewarded complexity and defense mechanisms. While these factors explain part of the story, they fail to account for the abruptness and completeness of the diversification. For millions of years prior, life had existed as simple, mostly microbial or soft-bodied organisms. Then in a blink of geological time, the seas teemed with complex animals fully equipped for predation, locomotion, and sensory perception. Here is where the Shadow Biosphere Hypothesis provides an intriguing lens. If life had existed in parallel, evolving along alternative biochemical or structural pathways, it is possible that some of these organisms interacted with the emerging carbon-based lifeforms in ways we cannot yet detect. These hidden ecosystems may have acted as catalysts, either through competition, cooperation, or environmental alteration, creating conditions favorable for the explosive diversification we observe. Perhaps previously hidden lineages were driven to extinction, leaving gaps that new life could occupy, or maybe their biochemical traces subtly primed the environment for rapid evolution. Fossil evidence from the Cambrian, such as the Burgess Shale in Canada and the Qinjiang deposits in China, provides tantalizing glimpses of life's diversity. These fossil beds reveal forms so strange that many defy categorization into modern phyla. Creatures like Hallucigenia, with its spines and tubular limbs, or Anomalocaris, a formidable predator with compound eyes and grasping appendages, suggest an evolutionary experimentation that was unprecedented. Could some of these forms represent interactions between familiar life and shadow life, organisms that survived only briefly before disappearing, leaving no descendants? The idea is speculative, but it cannot be dismissed outright when we consider the anomalies and missing transitional forms in the fossil record. Geochemical records also hint at complexities during the Cambrian period. Sudden shifts in carbon and sulfur isotope ratios suggest environmental upheavals, including dramatic changes in ocean chemistry. Some of these shifts could indicate previously unrecognized metabolic processes, perhaps tied to organisms with alternative biochemistry. If hidden biospheres existed before or during the early Cambrian, they might have left subtle chemical footprints in sediments and minerals, traces we misinterpret as random fluctuations or geological noise. Detecting these patterns requires an interdisciplinary approach, combining paleontology, geochemistry, and even theoretical biology. The Cambrian explosion also challenges our assumptions about evolutionary tempo. Traditional Darwinian gradualism, where small changes accumulate over time, struggles to explain such a sudden proliferation of forms. Yet if multiple biospheres or alternative life forms interacted, evolution might not have been acting in isolation. Hidden ecosystems could have created ecological pressures, chemical niches, or selective bottlenecks that accelerated diversification, producing what appears as an explosive event in the fossil record. In essence, the Cambrian explosion may not be a sudden leap from simplicity to complexity, but rather the visible emergence of life after long unseen preparation by parallel biologies. Further, the idea of a shadow biosphere coexisting during this period invites reconsideration of the very nature of evolutionary success. Traditional fossil evidence favors carbon-based, easily fossilized organisms. If alternative life forms existed but did not fossilize well, perhaps due to soft tissue, rapid CATI, or unconventional biochemistry, the apparent burst of life may reflect not just innovation, but the disappearance of hidden competitors. The record is biased toward those organisms that left traces detectable millions of years later. Thus, what we perceive as a sudden appearance could be the surface manifestation of a much longer, intertwined history. Even modern molecular studies provide indirect support for complexity predating the Cambrian. Phylogenetic analyses often suggest that many gene families and body plans originated earlier than the fossil record indicates. Molecular clocks place divergence events tens of millions of years before the Cambrian, implying that life was experimenting in obscurity, perhaps in shadow biospheres, before leaving recognizable traces. This raises the provocative possibility that the Cambrian explosion is less an origin story than a moment of revelation, the point at which previously hidden or suppressed life forms intersected with the dominant biosphere, producing an apparent rapid diversification. The Cambrian explosion is more than an evolutionary curiosity. It is a window into life's hidden potential, through the lens of the Shadow Biosphere Hypothesis. It may represent the intersection of known and hidden biospheres, the fallout of alternative evolutionary paths, or the chemical and ecological influences of life forms we have yet to fully understand. By studying the fossils, isotopic anomalies, and molecular data with an open mind, we may not only explain one of the most dramatic events in Earth's history, but also uncover the echoes of life that has always existed in parallel, quietly shaping the world beneath and around us. Atmospheric and geological anomalies as evidence. If the shadow biosphere has left traces, they might be written not in fossils but in the very chemistry of the Earth itself, its atmosphere, oceans, and crust. Traditional paleontology relies heavily on visible evidence, bones, shells, and impressions of past life. But what if alternative life forms left subtler signatures, embedded in minerals, gases, or isotopic ratios, that standard biology and geology have overlooked? The quest to detect hidden biospheres compels us to read the Earth as a chemical manuscript, where anomalies may reveal chapters previously unread. One of the most compelling lines of evidence comes from isotopic studies. Isotopes are variants of chemical elements that differ in neutron number, and biological processes often favor one isotope over another. Carbon, sulfur, nitrogen, and oxygen isotopes serve as telltale markers of metabolism. For example, carbon-12 is preferentially incorporated by photosynthetic organisms, while methanogenic microbes tend to favor lighter carbon isotopes. By examining ancient sediments, geochemists can detect unusual isotopic ratios that do not match known life processes. Some anomalies have been found in rocks over 3 billion years old, showing shifts in carbon isotopes inconsistent with known microbial activity. Could these represent the fingerprints of life forms with alternative biochemistry, now lost to the conventional record? Another avenue involves atmospheric gases trapped in ice cores, amber, and rock formations. Methane, oxygen, and carbon dioxide cycles have long been studied for clues about ancient life. Methane spikes, for example, often indicate microbial methanogenesis, but some anomalies appear too abrupt or chemically distinct to be explained by conventional microbes. Similarly, oxygen levels show sudden fluctuations in the geological record that cannot be fully reconciled with known photosynthetic activity. These discrepancies may be the subtle echo of shadow biospheres, ancient ecosystems operating on unfamiliar metabolic pathways that subtly altered the chemistry of the environment. Mineral formations themselves can also carry clues. Stromatolites, layered structures formed by microbial mats, provide some of the earliest evidence of life. Yet in some ancient deposits, unusual mineral laminations occur that resemble biological formations but do not match the known microbial processes. Could these structures be the work of extinct life forms with biochemical systems that did not fossilize in recognizable ways? Some scientists argue that rare isotopic and mineralogical anomalies in these formations hint at processes beyond our current understanding, perhaps involving organisms with alternative metabolic cycles or unknown biomolecules. Volcanic and hydrothermal environments offer additional insight. Presonal vents, hot springs, and deep-sea ridges have preserved chemical traces that sometimes defy simple explanation. Certain sulfur and iron isotope ratios suggest metabolic activity inconsistent with known extremophiles. In other words, the chemistry of Earth's crust may contain fossilized metabolism from organisms that we have not yet identified. Organisms that might belong to the shadow biosphere. These traces are subtle, easily dismissed as anomalies, yet they may be critical pieces of the puzzle in reconstructing hidden histories of life. Even contemporary observations provide hints. Unexplained methane emissions from deep-sea sediments, mysterious microbial activity in subglacial lakes, and anomalous chemical cycles in desert soils all point to the possibility that life operates in forms we do not fully comprehend. Could some of these processes be the modern remnants of a shadow biosphere? If so, we are witnessing a living echo of parallel evolution, a subtle yet persistent presence that challenges the boundaries of what we define as life. Geological events, too, could obscure the evidence. Mass extinctions, asteroid impacts, and tectonic shifts do more than reshape landscapes. They can erase the chemical signatures of entire ecosystems. A shadow biosphere, particularly if it operated in niche environments, might be obliterated from the fossil record, yet leave residual traces in the isotopic or mineralogical record. By focusing on these indirect markers, patterns in chemical composition, rather than physical forms, we may detect the fingerprints of ancient life forms previously considered invisible. Modern technology enhances our ability to investigate these anomalies. Mass spectrometry, X-ray diffraction, and isotope ratio monitoring allow scientists to detect extremely subtle differences in chemical compositions. Artificial intelligence and machine learning can help identify patterns in massive geochemical datasets that human researchers might overlook. With these tools, we can begin to distinguish between random chemical anomalies and the signatures of life, perhaps even life that existed alongside our own, yet followed a completely different path. Crucially, interpreting these anomalies requires open-mindedness and interdisciplinary collaboration. Chemists, geologists, microbiologists, and astrobiologists must work together to separate ordinary geological noise from meaningful biological signals. It is entirely possible that shadow life forms, intelligent, microbial, or somewhere in between, may have left marks so subtle that only a comprehensive, multi-layered approach can reveal them. Ultimately, the study of atmospheric and geological anomalies shifts our perspective of life on Earth. Instead of focusing solely on what we see, we examine the hidden chemistry that underlies ecosystems, past and present. These anomalies may be the whispers of ecosystems that existed before, alongside or in parallel with known life ecosystems whose intelligence, complexity, or unique biochemistry left traces that have persisted across eons. By decoding these chemical messages, we take another step toward uncovering the hidden biospheres that could reshape our understanding of life itself. The shadow biosphere and the human-Earth connection. The Shadow Biosphere Hypothesis is more than an academic curiosity. It challenges fundamental questions about humanity's place on Earth. If life, intelligence, or complex ecosystems existed alongside or before humans, then our narrative of being the planet's first sentient species is incomplete. This perspective forces us to reconsider the way we view evolution, ecology, and even our philosophical understanding of life itself. The implications are profound. Recognizing that Earth may host hidden, parallel, or previously unseen biospheres reshapes how we define intelligence, survival, and environmental stewardship. At its core, the human-Earth relationship has been framed around dominance and awareness. From the development of agriculture to industrialization, humans have assumed a linear hierarchy. We are the pinnacle of life, exerting control over the biosphere. Yet, the Shadow Biosphere Hypothesis suggests a far richer, more intertwined reality. If alternative life forms exist or existed, their presence may have influenced our development in subtle, unrecognized ways. Could certain microbial interactions have shaped the evolution of plants and animals, critical to human survival? Could ancient parallel ecosystems have set the stage for life as we know it, providing chemical, atmospheric, or ecological conditions necessary for our emergence? This connection extends beyond mere speculation. Modern science increasingly recognizes the intricate dependencies between humans and microbial life. The human microbiome alone, trillions of bacteria, viruses, and fungi inhabiting our bodies, demonstrates how deeply interwoven our survival is with unseen organisms. Shadow biospheres operating in parallel could represent similar planet-wide networks of influence. These hidden ecosystems might regulate nutrient cycles, mediate atmospheric chemistry, or stabilize global climates in ways we barely understand. By studying them, we gain insight not only into life's diversity, but also into the systems that sustain our own existence. Philosophically, the existence of hidden life forces humility. Humanity's self-image as the apex of intelligence is tied to the assumption that we are the first to achieve consciousness or civilization. If parallel biospheres or intelligent species existed in Earth's past, or even persist today, we must acknowledge that intelligence is not uniquely human, nor necessarily carbon-based, nor necessarily biological in familiar forms. This realization broadens our conception of sentience, encouraging us to see intelligence as a spectrum rather than a pinnacle, and urging caution in our interactions with ecosystems that might be far older, more complex, or more resilient than we imagine. The shadow biosphere also reframes environmental responsibility. If hidden life forms exist or existed, human activity, deforestation, mining, pollution may be impacting unseen systems in ways we cannot fully comprehend. Some chemical disturbances, unexplained ecological collapses, or subtle atmospheric changes could reflect interactions with these unseen biospheres. Recognizing this possibility does not simply expand scientific inquiry, it instills a moral imperative. Humanity's stewardship of Earth must account for not just visible life, but the potential for hidden or alternative ecosystems that could hold keys to planetary stability. Moreover, examining the human connection to the shadow biosphere encourages us to explore the boundaries of our own biology. Could humans coexist with alternative life forms in ways not yet understood? For example, extremophiles survive in conditions lethal to humans, yet microbes from shadow ecosystems may inhabit niches within our environment or even within our bodies, contributing unknowingly to health, immunity, or disease. The interaction between visible and hidden life forms could offer insights into biotechnology, medicine, and ecological management, revealing a network of life in which humans are participants rather than solitary dominators. Historical anomalies, too, take on new significance. Artifacts, mysterious fossils, and geological oddities that previously seemed unconnected may gain meaning when interpreted as part of a broader shadow ecosystem. Ancient civilizations might have encountered remnants of these life forms, leaving hints in myth, ritual, or early observations of nature that we have long dismissed as folklore. Recognizing these interactions challenges the narrative of human exceptionalism and reframes the study of history as intertwined with a broader biospheric complexity. The shadow biosphere also has implications for future human evolution. By studying hidden life forms, microbial extremophiles, alternative biochemical systems, or parallel intelligent species, we may uncover strategies for adaptation, resilience, and survival that exceed the limits of conventional biology. Could insights from shadow life forms inform gene editing, synthetic biology, or sustainable ecological management? Could understanding alternative metabolic pathways help humans adapt to extreme environments from deep oceans to other planets? The lessons are potentially transformative. Humanity is not isolated, and our understanding of life is incomplete. The existence of shadow ecosystems and hidden histories emphasizes interconnectedness, humility, and curiosity. By embracing the possibility that unseen forms of life shape the Earth, we expand both our scientific horizon and our ethical responsibility. The human-Earth connection is no longer a simple story of dominance. It becomes a complex, layered narrative in which humans are one actor among many, part of a dynamic, mysterious, and potentially multi-layered biosphere. This perspective shifts the way we ask questions, design experiments, and engage with our environment. It calls for an integrative science that looks beyond the visible, explores chemical and ecological patterns, and redefines life as something broader than the carbon-based, DNA-centered paradigm. By doing so, we honor both the seen and the unseen, recognizing that Earth's history and our place within it may be far more intricate and wondrous than previously imagined. Breakthroughs in detection. New frontiers in science. The quest to uncover a shadow biosphere requires innovation at the very frontiers of scientific exploration. Traditional methods, fossil analysis, standard microbiology, and conventional biochemistry may be blind to life that operates outside known paradigms. Detecting hidden or parallel life forms demands cutting-edge technologies, interdisciplinary approaches, and a willingness to challenge established assumptions. Modern breakthroughs in detection are creating tools that may finally allow humanity to explore these uncharted biological realms, revealing organisms and ecosystems that have remained invisible for eons. One of the most promising avenues is advanced metagenomics. Unlike traditional microbiology, which relies on culturing organisms in the laboratory settings, metagenomic sequences all genetic material in a sample directly from the environment. This allows scientists to identify organisms that cannot be grown using standard techniques, which is particularly important when searching for life forms with unconventional biochemistry. By analyzing soil, water, or even deep-sea sediments, researchers can detect sequences that defy classification, hinting at microbial lineages that might belong to a shadow biosphere. These dark genomes challenge our understanding of biodiversity and suggest that vast branches of the tree of life may remain unexplored. Beyond genetic analysis, isotope geochemistry provides another critical tool. By studying isotope ratios in carbon, sulfur, nitrogen, and oxygen, scientists can detect metabolic processes that differ from those of known organisms. For example, a life form that metabolizes arsenic instead of phosphorus would leave a distinctive isotopic fingerprint. Similarly, unusual sulfur or nitrogen cycles in sediments might indicate life that doesn't conform to standard metabolic pathways. When coupled with high-resolution imaging and spectroscopy, these chemical signals can reveal hidden ecological activity, even in environments previously considered sterile, such as deep subsurface rocks or isolated hydrothermal vents. Artificial intelligence, AI, and machine learning are increasingly central to the detection of hidden life. These algorithms excel at pattern recognition in massive datasets, finding correlations and anomalies invisible to human researchers. For instance, AI can analyze satellite data, mineral composition, and chemical signatures across continents to identify regions where shadow ecosystems might persist. It can also sift through genomic sequences to identify non-standard coding patterns, revealing organisms that traditional algorithms would discard as noise. By leveraging AI, scientists can accelerate the discovery of life forms that defy conventional categorization, detecting patterns that might otherwise remain hidden for decades. Microfluidics and single-cell analysis offer additional breakthroughs. Life in extreme environments or shadow ecosystems may exist at extraordinarily low densities, making it difficult to detect using bulk sampling. Microfluidic devices allow researchers to isolate and analyze individual cells or microcompartments of environmental samples. This enables the study of rare organisms, measuring their metabolism, biochemical composition, and even potential intelligence-like behavior. Single-cell studies can reveal alternative biochemistries, unusual replication strategies, or unknown metabolic cycles, directly probing the possibility of life that does not fit the traditional carbon-based, DNA-dependent mold. The rise of synthetic biology also offers a unique perspective. By constructing artificial life in laboratories, scientists explore the fundamental rules of biology, testing alternative biochemistries and metabolic pathways. This work informs the search for shadow life, providing models of how non-standard life forms could exist in the wild. Synthetic analogs, organisms designed with silicon-based backbones, modified nucleotides or novel energy cycles, help researchers recognize patterns and chemical signatures that might otherwise be overlooked. In essence, synthetic biology creates a roadmap for detecting forms of life that evolved under entirely different rules. Remote and extreme environments remain a key focus. Deep-sea exploration, ice core drilling, and subsurface sampling allow access to locations where shadow ecosystems might persist undisturbed. Hydrothermal vents, subglacial lakes in Antarctica, and hypersaline brines in deserts or salt flats provide laboratories for discovering life forms that could not survive elsewhere. These environments mirror conditions that may have existed billions of years ago, offering the possibility that relic shadow biospheres, either microbial or more complex, still operate today, hidden from human observation. Interdisciplinary collaboration is crucial to these breakthroughs. Chemists, geologists, biologists, computer scientists, and astrobiologists must work together to design experiments, interpret subtle anomalies, and distinguish true biological signals from background noise. This collaborative approach enables the development of more sensitive, precise, and comprehensive detection systems, capable of revealing ecosystems that have remained invisible for millennia. Finally, space exploration itself informs detection strategies on Earth. Techniques developed for astrobiology, searching for biosignatures on Mars, icy moons like Europa, or exoplanets, provide models for detecting hidden life on Earth. Instruments designed to identify chemical anomalies, energy fluxes, or metabolic byproducts in alien environments can be repurposed for terrestrial applications, helping to uncover the shadow biosphere in ways previously unimaginable. The frontiers of science are converging to make the invisible visible. From metagenomics and isotope geochemistry to AI, microfluidics, and synthetic biology, humanity now possesses an unprecedented toolkit to explore hidden ecosystems. These breakthroughs not only enhance our understanding of Earth's biosphere, but also challenge our assumptions about what life is, where it can exist, and how it might persist in parallel with the life forms we already know. By pushing these boundaries, we move closer to unveiling the full complexity of life on Earth, and perhaps finally discovering the echoes of the shadow biosphere that have remained hidden for billions of years.